All right, let's start. The first question is about alkenes. Alkenes contain a carbon-to-carbon double bond that consists of a sigma bond and a pi bond. So they basically told you to complete the diagram to show the areas of the electron density for each bond. So you have to label the sigma bond and the pi bond basically right here. They told you. We know that how is a sigma bond and a pi bond being produced? Well, a pi bond is produced due to what? The sideways overlap of p orbitals, isn't it? Do we know this? Please respond. Sylvia, do you know this? So what happens is pretty simple. The electrons present right here, they basically overlap something like this, resulting to the production of a pi bond. Okay. The next thing's pretty clear. We need to show the sigma bond basically, and so the sigma bond is basically produced by now production of sigma bond. There are so many ways you can produce the sigma bond. The most common way is one of the most common way is, you know, the end on overlap of the p orbitals. That's how a sigma bond is produced. Okay, there is another combination, basically the overlapping of an s orbital and what, a p orbital. So an sp overlap or a pp overlap, these are ways in which a sigma bond can be produced as well. Okay, there is another way which is I forgot. The overlapping of two s orbitals as well may also result to the production of a sigma bond. So whatever that is, this is rare. All right, this is rare, but pp overlap and ss overlap is the most common one, the common ways or the common combinations in which sigma bonds are produced. So you just use any one of them. You can just use this combination or this combination. So let's just use the first one to show the sigma bond. There you go. So electrons are shared here, and this results to the production of sigma bond. All right, did you understand this topic chapter? I mean, this question. I hope you did. Next part is propene. Now, propene is an alkene. The reagents required for three reactions of propene, they told you. So they have been provided you propene. All right, fine. Now they told you what? They basically told you that what is basically produced with steam when you basically pass propene through acid steam, acid catalyst and steam basically. And what happens when you oxidize it using acidified potassium manganate 6, and what happens when you add bromine to it. All right, now when we add bromine, we know which reaction takes place. Electrophilic addition reaction, right? I mean, that is the mechanism, isn't it? So basically an addition reaction takes place. All right, so basically what's going to happen in this case? In this case, the bromine are going to get connected. Both of the bromine atoms are going to get connected, and they're just going to get added to produce this one right here basically. Okay, so this is the answer for this one. Just an additive product. Since it's an addition reaction, nothing is substituted. You can also give this to bromine on the you can also give this bromine on here as well if you want, no problem, but it kind of means the same thing. Now what happens when you basically pass an alkene through an oxidizing agent? Well, when you pass alkene through an oxidizing agent, you are oxidizing it, right? That means you are adding an oxygen or an hydroxyl group. Most probably you are adding an oxygen basically, isn't it? You are adding an you are basically adding an oxygen basically. So if you do that, what happens? The double bond basically obviously breaks down for accommodating the oxygen, but obviously the oxygen won't just come like this. In this case, the oxygen will come in the form of hydroxyl group. Okay, so OH, Now, there is a difference here. You have to understand this is a strong oxidizing agent. So basically, it has the power, or it has the power to basically, add up to at least two oxygen, all right, to a alkene. If you would have used another oxidizing agent which was a weaker one, then only one hydroxyl group might have been added. But since it's a strong oxidizing agent, so we'll be adding another OH. So eventually what is produced in an alcohol is produced, but this type of alcohol is known as what? Can anybody tell me what type of what do we name this type of compounds which have two OH groups in them? Can anybody tell me? Does anyone has any idea about it? Simra, Sylvia, anyone? Exactly, diol. Very good, diol. Yes, Simra, please raise your hand. Say. You want to say? Oh, no, no, I could hear you. No problem. Okay, so that's diol for you. And if I talk about when you basically, pass steam along with acid catalyst, what happens? Well, the thing that basically happens is that again, an alcohol is produced, but it's this time here, obviously, steam is not an oxidizing agent. It's basically acting just as a source of oxygen, like for instance H2O, which means HOH. All right, so what is happening here is pretty simple, right? The OH is being donated here. So since there's only one OH, so obviously what's going to happen? One of the hydrogen atom, let's say from this one, will be replaced by this OH. All right, and the H which got replaced, it will react with this H and produce the byproduct hydrogen, which we do not have to write. All right, so I hope you understood. These are the three products. Okay, did you guys understand this one? Please tell me. Ilham, Sylvia. Yes, yes, you can, no problem. Propene also reacts with hydrogen bromide. Now you should give the mechanism for this reaction to form the major product and also show what? The curly arrows. Okay, we know what it is basically. What I forgot. Electrophilic addition, right? The mechanism is electrophilic addition reaction. So what happens? Pretty simple, right? Let's draw this out. So what is happening down here? Well, we know what the double bond consists of an high electron density, meaning it has shared pair of electrons right here. What does it have? High density of electrons, making it negatively charged, isn't it? Yes. So since it is negatively charged, so whenever the nucleophile comes to attack it, now we know who is the nucleophile here. Obviously, HBr. Sorry, no, we know who is the electrophile here. HBr. Why am I saying electrophile? Because it's electrophilic addition. It's going to be an electrophile. It's going to act as an electrophile. So what happens here is pretty simple, that when the electrophile HBr comes near to this high electron density double bond, carbon to carbon double bond, it tends to attack it. Why does it tends to attack it? Because obviously it is negatively charged and our hydrogen here is positively charged within the electrophile. So this tends to attack the double bond as it gets attracted towards it when it comes near, when the whole electrophile comes near this region. All right, so at the same time, what happens? Something great happens, which is via heterolytic fission, this bond breaks down. And we all know what is heterolytic fission. Sylvia, can you tell me what is heterolytic fission? Any idea? Sylvia. All right. Heterolytic fission is the process in which bonds are broken Did you understand the whole? It's basically the process in which bonds are broken by the absorption of bonded electrons by the higher electronegative element in that bond, forming radicals. Radicals is what? We all know what? H plus and Br, this one, right? We basically represent radicals by showing an unpaired electrons right here. All right. Okay, you can show, you can either show it in this way, but we don't actually show it here. Like, I mean, you can show this one, I mean, you can show the unpaired electron like this, or you can just simply show it like this as well. All right, any one way you can show, it doesn't matter how you can show radicals. So what are radicals? Radicals are species which consist of unpaired electrons. So did you understand what is heterolytic fission? In this case, bromine is more electronegative than hydrogen, and that's why it has the power to take out most of the bonded pair of electrons during the breaking. Did you understand? Okay. Yes, because bromine is the higher electronegative element here. Did you understand? It's not only bromine, it could be chlorine, it could be fluorine, it could be any halogen. Did you get my point? All right, I'm erasing this. I hope you have guys have written this. It's very important whenever I write small notes. It is an unspoken rule, but you should write it. All right. Okay, it's gone. Fine. The first step is clear. Now, what is the second step? Well, in the second step, what is produced when this bond, when it attacks? What is happening here? This heterolytic, by heterolytic fission, this bond is being broken, and at the same time, something great thing is happening. This double bond also breaks when this electrophile attacks. All right, this is the electrophile. We all know what is in electrophile, right? A species which is positively charged. A species which is positively charged and is attracted towards a high electron density region. All right, so the species, the electrophile, in order to identify electrophile, you just need to check two conditions. The species itself is positively charged and it is attracted towards a high electron density region, in this case that carbon to carbon double bond. All right, so the next part is pretty simple. What happens? Again, here a carbocation is basically produced. All right, they told you to show the major product. Okay, one thing's clear. There are two ways this this reaction might go. Have you guys written the electrophile definition? The ones who are confused, should I erase it? Ilham, Sylvia. Okay, okay, okay. Let's move on. So there are two ways that might happen. The carbocation might be produced here, or the carbocation might be produced there. All right. Now, bhaiya, question might arise: which one is the major and which one is the minor product? See, I think we know this pretty clearly, that the stability of the stability depends on the degree of carbocation, which in this case this is the trend. All right, the stability, this is the trend stability of carbocation. So what happens in the trend stability of carbocation? A third degree carbocation has what? The highest stability in compared to the second degree one, in compared to a first degree one. All right. So if we check out in these two cases, who is the second degree carbocation here? This one, right? The first one, isn't it? Ilham. And this is what? First degree, and this is second degree. So who do you think the more, remember all the time, the more stable product is the one which contains the higher degree carbocation. Did you understand? So the more stable the product, The stable, the what's it called, the more stable product is the one which contains higher degree carbocation, and the more stable product will be the major product. This will be, yeah, continue. Okay, so it's pretty simple. If we check this out right here, if the carbon, remember, if the central carbon where the carbocation is produced, I mean where the carbocation, let's say the carbocation is produced here. Now if this carbon is connected with three other carbons, then it's third degree. All right, let's say the carbocation has been produced. If this carbon is connected with two carbons, then it's a second degree. If this carbon is connected only one carbon, then it's first degree. Did you understand how you distinguish third, second one? Okay, I hope you do. So obviously, who is the more stable product? Yes, 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 yes. What do you mean by four carbons? There is no possibility of fourth carbon, bhaiya, because the fourth part is a carbo is a positive. It's a carbocation. How can there will be fourth carbon? Maximum you can add three carbons with the carbon which contains the carbocation. There is no fourth bond here, isn't it? I think you can understand the logic behind, right? So there is no chance basically. All right, that's gone. What is now the next part? I have written everything. I hope you have written these statements. Have you guys written this? Should I erase? All right, I'm erasing. You can check the video if you want later on. So who is the major product? Obviously the second degree one is the major product, so we can just omit the minor product, the first degree carbocation, and just continue with this one. So the next part, what happens? Well, the what happened, the bromine which came out, now this guy will attack. All right, and eventually the last stage is what? The main product. All right, so the main product here would be, what will be the main product? Br. Yes, this is the answer. All right, this is how you basically show the mechanism. Remember one thing. Okay, I think the arrow sign is mistake. That this, when you show the attacking of the electrophile, the arrow sign should be pointed towards the electrophile. Okay, this is very important. One thing. Arrow sign showing electrophile attacking. All right. So this is how you basically show the mechanism. I hope you guys understood. And I think you can understand the lone pairs and dipoles. Well, what is the lone pair here? This is the lone pair that they're talking about. And what are the dipoles? The dipoles are these ones which were produced: partially positively hydrogen charged hydrogen, and partially negatively charged bromine. All right, I hope you guys understood. Everything is showed. The Cardi arrows are also shown. These are the things that they expect you to write, to draw, actually, to be honest, while showing a mechanism. All right, moving on to the next part. Alpha-ocimene contains three carbons to carbon double bond. It is found in plants and has a sweet smell. The skeletal formula is shown right here. Can anybody tell me what is the molecular formula of this? Please count and tell me fast. It's very simple. Sylvia, please try. Sylvia, are you there? Even Simra, you can try as well. No problem. Let's see in competition who can do it. Make sure it's correct, by the way. Fast, it shouldn't take that much time. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. Done. Was it that hard? And then we just need to check out the number of hydrogens, right? So we have what? If you draw here, 1, 2, 3, 4. No, 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 there's nothing here. There's nothing here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 8, 16. That's the answer. Did you guys get that? On the skeletal formula, draw a circle around the part of a molecule that provides the rise to the geometric isomerism of alpha oximine. Okay. Well, I guess it's pretty simple, right? Can anybody tell me which part? Please do not choose this part and this part down here. Because why? Because check this out. This carbon and this carbon right here, both of them have two identical hydrogen atoms attached. All right. And if you if you have clear and sharp idea about geometric isomerism, particularly the what's it called, cis trans isomerism, particularly speaking, what happens is that there are two conditions. All right. What are the two conditions for cis trans geometric isomerism to happen? Well, the first condition is pretty simple. The two carbons in the carbon to carbon double bond, one carbon cannot contain two identical atoms. All right, this is the first condition. And the second condition is that there must be unrestricted rotation. All right, unrestricted rotation along the plane of the carbon to carbon double bond, meaning that the whole thing cannot rotate, that this bond and this bond cannot rotate and exchange their places. All right, these are the two conditions. Well, if the even though the second condition met, the first condition is not met for this carbon and this carbon right here, because you can clearly see what, that you can clearly see, sorry, actually, yeah, you can clearly see that two hydrogens are connected, so that is not the correct answer. So the only double bond present in this molecule is this one. All right, so this is the part which is going to show you geometric isomerism. I hope you understood. Draw the skeletal formula of the other geometric isomer of alpha oximine. Okay, okay, if you want to draw this, all right, Sylvia, can you try tell me what's going to happen? What is the change here? Can you tell me? It's pretty easy since I've already showed you from which part the geometric isomerism is gonna rise. Only this part is gonna change and this part is gonna change, isn't it? Because you can clearly see what, this is the part which is going to show geometric isomerism. That means this is our guy and this is our guy. Did you understand? Okay, so what's going to happen? Just interchange, nothing else. So if interchange by that means this one will go up. That means this one is gonna go up. Gone. And what's going to happen? That guy is gonna go down, I believe. Yeah, that guy is gonna go down. Like this part right here. So something like this. Yeah. So I brought this guy down and I took this guy up. But that's it. Nothing else basically. So this is the other geometric isomer of alpha oximine. In an experiment of 0.050 of alpha oximine reacted with 3.6 dmq of hydrogen in the presence of a catalyst, you should deduce the structure in this reaction. They told you to deduce the structure of the product of this reaction. All right, let us at first calculate the moles of hydrogen first. It's pretty simple, right? How do you calculate the moles of hydrogen? You just basically, we know that 1 mole provides 24, so actually 24 provides 1 mole. So uh so how much does 3.6 dm cube provides? You basically just divide 3.6 by 24 by 24. That's equal to 1 mole. Eventually you get about 0.15 mole, I believe. Yeah, it's 0.15 mole. So now you just, now one thing is pretty sure, that now what to do is that we just need to calculate the number of carbon to carbon double bonds present in this oximine structure, because we know that alpha oximine is what? Alpha oximine is this is alpha oximine, right? So when you add hydrogen, what is happening? And hydrogenation reaction is happening. That means these bonds will get broken down. So now let us at first find the ratio first, like how many carbon to carbon double bonds are broken down. We need to ensure that, like the number, it's kind of simple, that the number of carbon to carbon double bond hydrogen bonds, the number of carbon to carbon double bonds being broken down is equal to the number of hydrogen bonds being added. Am I clear? All right, I hope you understand this. So how will we find this? How many number of, how many carbon to carbon double bonds are broken? Well, you can just just find the ratio. You can just find the ratio of hydrogen mole divided by, they said what, they already provided you the mole of alpha oxime, the ratio of hydrogen mole and alpha oximine mole. All right, you just find the ratio basically. So it is what, 0.15 divided by 0.050, which is provided right here, and I just found that one here. So eventually you get what? If you divide it, I get 3. So 3 here represents the number of carbon to carbon double bonds being broken. So that means we had 3 double bonds here, so 3 of them is gonna get broken down. And so our new structure would be what? If you just break out these bonds, so what comes? uh not this, not this structure, this structure, not this structure, this structure. So if these 3 bonds get broken down, what comes? You have this one. Oh yeah, does it make sense? Yes, it makes sense. So see, I have just broken down the bonds right here, this one and this one and this one. Okay, did you guys understand? Hello, why is nobody responding? All right, moving on to the next part. Which of these is not a way of global problems caused by polymer disposal? Okay, it's not a problem, they say basically. All right, so in this case, what can we say? All right, try this. Simra, can you try this and tell me? You said B, exporting polymer waste, right? Okay. All right, I understood your concept, but why do you think you did not choose A, C, and D? Okay, developing biodegradable polymers. Well, first of all, uh, this is an I mean, this does not, this does not basically, I mean, this limits, like if you what happens is that biodegradable means what? It can be, decomposed by microorganisms, isn't it? Right? So if they can be degradable or broken down by microorganisms, so it is kind of limiting global problems, all right, which are caused by polymer disposal. Because most polymers are what, non-biodegradable, but if you make them what, like but if you develop polymers which are basically biodegradable, so in a sense that when they are disposed as waste, they can be, decomposed by microorganisms, all right. So that kind of limits the global problem, so that is not the correct answer. See, removing toxic waste gases produced by incineration of polymers. So when you burn polymers, incineration basically means burning. I think you have seen this before a lot of times in Bangladesh, if you were here, that basically burning of polymers results to the what? It's basically what it removes, the toxic waste gases which are produced. If the toxic waste gases are removed, what are the toxic waste gases here? You have carbon dioxide, carbon monoxide. If these are removed, so it kind of also limits the global problem. And reusing products made from polymers, basically recycled, so that is another solution to this global problem, so it does not act as a limit. Now this is not a way of limiting global problems, because if you simply export polymer waste without refining it, then it's not going to, limit the global problem. So I guess yes, B is your correct answer. All right, Sylvia and Elham, did you understand? Okay. Okay, up to this much for this topic. We are going to move to topic 2. Give me 1 minute. I'm going to give this PDF for, homework basically, all right. And if you solve this PDF, I hope you will be able to finish 2022, 21, 22. Just remember one thing, these PDFs are very important. I think Simra and Ilhan did them, right? In the case of Unit 2, these are just like Unit 2 worksheets. Am I clear, Ilham and Simra? And I'm just telling this to Sylvia as well, that if you solve these worksheets which I have provided you, I think I have provided you one worksheet, Sylvia. Have you checked that out? Yeah, so these worksheets are very important, consisting as you because these worksheets consist, questions topic wise from 2022, 2021, and 2020. So by doing these worksheets, you are basically doing these three of the papers. Am I clear? So it's very important, one thing. And Sylvia and Simra, I hope I think you know this, right? So please do them as well. I will send you. Okay, so I'm going to the next topic, which is topic 2, atomic structure and periodic table. 1 minute. All right, let's start with topic 2. Okay. Element X is in group 2 of the periodic table and element Y is in group 7. Now X and Y are not symbols of these elements. Alright, now they said here, what is the formula of the compound formed from X and Y? Alright, first of all, we know that group 2 are what? Metals. Alright, and group 2, what's it called? Group 7 are non-metals. Can you guys hear me? Sorry, I was, I think, muted. Sorry about that. Look, element group 2 is basically metals, and group 7 are non-metals. All right. So if this is the case, so when what do metals do? They basically lose electrons, right? So whatever it is, it will become X plus, and non-metal is going to be Y minus. All right. Now, since it's in group 2, that means the at most it can lose electrons is what? 2 electrons, right? So it's going to be X2 plus. And we know that what? Y is in group 7, isn't it? At most it can gain one more electron. All right? At most it can. So it's going to be Y minus. So when you basically combine them, they basically, if you combine them, what happens? The valence is basically X2 plus and Y minus. The valence is swapped, and eventually you get XY2. So our answer will be C. Did you guys understand? Under what conditions does the compound form from X and Y, conduct electricity? Okay. Uh, X and Y, as we can clearly understand, it's an ionic compound. So we know that ionic compounds do what? They only and only basically, they can only do it in their what? Can anybody tell me? In their liquid and aqueous solution, right? So not in solid state. In three of these options, you can clearly see that solid state is provided as an option. So obviously, automatically, D is the correct answer because the ions are mobilized or they are mobile in this state. Which of these compounds would you expect to have the highest melting temperature? Okay. First of all, you need to check which one is the most polar bond here. Can anybody tell me which one is the most polar bond? Now look, check this out right here. You have NaCl, KCl, KF and NaF. We know F is the highest electronegative element in what's it called? In the whole periodic table, right? So we are going to exclude NaCl and we are going so and KCl out of the box. We just need to ensure B and we just need to check B and D here. All right. Now, both of them obviously, since both of them contain F, so both of them obviously will be what? Like their electronegativity is high, so electronegativity is not taken into a consideration. Now, this basically, and both of them are what? Ionic bonds, isn't it? Now, we just need to determine the strength. Now, how do you determine the strength of this ionic bond here? All right. Well, you just need to check out, like, since the anions are same, we just need to basically analyze the cations. Now, who has a larger ionic radius? Can anybody tell me? Na plus or K plus? Na plus or K plus? K plus has a larger ionic radius, isn't it? Because K is down the group, isn't it? Yes, yes, exactly. So this is the problem, all right? So what is happening? This has a larger ionic radius, all right, and this has a smaller ionic radius compared to this. Now has I think what is the rules of polarization? This polarization, right? Yes. Polarization, the rules of polarization is pretty simple. In case of smaller size cation and high charge, what increases polarity. Large size anion increases polarity. All right, these are known as the what? Fadam's rule. Have you guys heard about it? Simra? I said this is known as the Fadam's rule. Have you heard about Fadam's rule of polarization? And this is known as the charge. This is the equation of the charge density. Check this out. If the cation has a smaller, if the cation is smaller in size, what is happening here? The charge density is increasing. All right. Now everything depends on the charge density. So if the charge density increases, then if the charge density basically increases, so the r square, if the cation, what's it called, if the cation charge, if the cation size decreases, then what happens is the charge density increases, and this basically results to the polarization, a higher polarization basically. And higher polarization means what? A higher polarization basically means, sorry, what's it called, 1 minute. Yes, a higher polarization. mm, yes, a, a higher polarization will lead to greater covalency and less ionic bonding. All right, now since the anion is same, I mean in case of F and F, the anion is same, so this fact factor is not taken into consideration according to the Fadhan's rule. So the only factor which is taken is the cation factor here. All right. So you can clearly see that obviously anion sodium has a smaller size cation, right? So if it is a smaller size cation, its charge density is going to be higher, and what what is going to happen? It is going to receive higher polarization. This will lead to greater covalency and less ionic bonding. So our answer will be this one. This will have the highest melting temperature. Did you understand, all of you? Hello. All right. Now, a drop of an aqueous solution of green copper to chromate 6 is placed in the center of a strip of damp filter paper. The ends of the filter paper are connected to a DC power supply. All right, they said this. Very nice. They said are connected to DC power supply. What is after observed after a few minutes? A green color has moved to the negative end. A green color is moved to the positive end. Now, A and B is not correct because there are two colors here involved. We just need to check that out. The yellow color is from chromate ions, while the blue color comes from the copper 2 ion. All right. So there are two colors involved. So A and B is not correct. We just need to check out C and D right here. Uh, so it's what? Cr. It is what? Cu. Chromate is chromate 6. So CrO4 basically. All right. So this one itself is negatively charged, and this one itself, I believe, is positively charged. So since the yellow color is if the yellow color is from here and this one comes from blue, so the blue color is supposed to move to the negative end, and the yellow color is supposed to move to the positive end, considering this is negatively charged and this is positively charged, and we know what unlike charges attract. Am I clear? Did you understand why C is the correct answer? Hello, did you? All right. which of these iso which of these isoelectronic ions has the smallest ionic radius? Okay, Simra, can you try this? Which one? Isoelectronic means what? Four of these ions have the same number of electrons, isn't it? Now everything depends on what then? The number of protons, right? Am I clear? Hello? So can you tell me who has okay, now the smallest ionic radius, higher the nuclear charge, smaller the ionic radius. And how do you increase the nuclear charge? Greater number of protons, right? Now tell me who has the greatest number of protons among these four ions. It's pretty simple, isn't it? Yes, aluminium is the correct answer. D. Did you understand how I approached this question? This question is about copper and its compounds. Complete the electronic configuration of Cu and Cu2 plus. This is very easy peasy, I believe. Okay. You can check the periodic table if you want and also do it. No problem. So what is it? I believe argon is 18. So 3D 10, 4s 1. All right. 18, 28, 29. Yes, makes sense. Because zinc is 30. And this is 3D 9. Considering 2 electrons go away. So yeah. This is so easy basically. It's like IGCSE question. So it's what? 29, 29. And then if you just find the neutrons, I believe it is 29, 29, 34 and 36 if you just do it. What are isotopes? Can anybody tell me what are isotopes? Tell. Very simple. Ilham, tell me. And also use the information from the table. Fast. Ilham, are you there? Same number of protons but different number of neutrons. Very good. Yes, that is the correct answer, to be honest. uh, I'm not writing it. I hope you understand this. State why the two isotopes of coppers have the same chemical reaction. Okay, again Ilham, answer. Why do you think isotopes have the same chemical reactions although they have different neutron number? First of all, you tell me, does neutron number play a play a huge role in determining the chemical reaction? No, right? It doesn't. So what plays an important role? Tell me, electrons or protons? Yes, exactly. So all of them have the same number of electrons. That is the reason. Do you understand? I don't think this is so easy. This is IGCSE math. Okay, Sylvia, tell me, how will you do this? Very simple. Sylvia, how do you do this? This is IGCSE math. I hope you're supposed to do this. Very simple. They have provided you the relative atomic mass, right? How do you find the relative atomic mass? You basically multiply the percentage atomic mass. What you basically with what the mass numbers, isn't it? Now you don't know the percentage abundances, right? You are supposed to find it, isn't it? So let's choose x. Let x be the percentage abundance. All right, so let's give like what, let's say for instance x times acha, let's use this one, x. And now okay, one thing's pretty sure, we know that what x is within 100%, right? So if one of them is x, that means the other one will be 1 minus x, isn't it? Like if you just subtract it from 100%, isn't it? Did you understand what I'm trying to say? Like say for instance x is 70%, so 1 minus x is that one. I hope you understood that. So times, this is times what, 60, let's say 63, and in this case of times 65, let's say, and then you divide it by what, 1. Okay, if you want you can just divide it by 100 times 100, so eventually you will just cut this out, you'll get what, 1, right? Isn't it? Because this is a percentage. Am I clear? You're supposed to find the percentage, isn't it? So that's why you need to multiply it by 100. So and eventually you'll get what, you'll get 1. Now you just solve for x and get x value. Am I clear? And after you get the x value, you get the y value by what, 1 minus x. Did you get the point? X and y are your percentage abundances. Did you get it? See, when, okay, check this out. When you solve for x, what comes? Do you know? When you solve for x, in my point of view, I get 0.8. Okay, I get x about 0.8. All right, 0.80. Basically, if you just multiply it by 100%, you will get 80%. All right, that is the abundance. So that's why I give 1 minus. That means the rest. I mean the rest of the percentage abundance is dominated by what? This is what. Let's say this is what, 60. This is 65 one. I mean copper Cu65 abundance. All right, 80%. That means the rest is basically what, dominated by Y, isn't it? 63. Did you understand? 20%, 0.20. Am I clear? Which you can just multiply by 100 and get 20%. Did you get it? Why I give 1? Copper to sulfate can be made by reacting solid copper to carbonate with dilute sulfuric acid. They say it down here. Okay. Write an equation for the reaction that occurs and state the state symbols are not required basically. So this is like the, you can check this out. You can, this is like the, you can write any one of them if you want. This one. You can just show any one of them if you want. Did you understand? And yeah, what's it called? Ilham, did you see how they basically came to this part? The writing the ionic equation, you had problem, I believe. Did you see what they did down here? Look, this is what? This is solid. So you cannot break it down. But this is aqueous, right? So you can break it down. And we know SO4 and SO4 are what? Spectator ions, isn't it? And spectator ions can be what? Cancel down. And this is G and this is L. Remember, Gl, these gaseous and liquid forms, they cannot be broken down as well along with solid form. The only thing that can be broken down into simpler ions is aqueous forms one. Did you understand? And I guess Sylvia, did you understand this? Okay, now that's a big question basically. Read this for 1 minute, I'll show. All right, I hope you have read this. So they told you to basically find what? They told you to basically find the percentage yield for this reaction. At first, let us at first calculate the moles of sulfuric acid with the provided data. So we have 50, right? So was it? Yeah, yeah, sulfuric acid. So moles of sulfuric acid is pretty simple. 50 by 1000 times 1. Eventually you get about 0.05. So you got the moles of H2SO4. Now you can calculate the maximum mass of copper 2 sulfate. How much copper 2 sulfate can be produced? So like you have already what? Like you know the mass, smaller mass of copper 2 sulfate. So you can write, just write that how much moles of you were used, this much moles of H2SO4 was used for the production of copper 2 sulfate 5H2. So the maximum moles, right? Sorry, actually mass. Maximum mass of copper 2 sulfate, multiply this 0.05 times 249.6. Eventually you get what? Eventually you get about 12.48, I believe. 12.48 gram maximum of copper 2 sulfate that has reacted. Okay, so now we know what? We know the actual yield, isn't it? Yes or no? Sorry, not actual. We know the theoretical yield, right, Simra? Isn't this the theoretical yield? All right. We know the theoretical yield. And what is the percentage yield formula? Actual, actually it's the opposite. Actual divided by theoretical. Did you get it? You made the opposite mistake. Actual divided by theoretical times 100. So it's pretty simple, right? So 12.48 and above you got 10.87 times 100. Eventually you're gonna get about 87.1%, I believe. That is the answer, the percentage yield of this one. Did you understand, Ilham? All right. Sylvia, did you understand this process? Check this out. What I did down here, I basically found the maximum mass of CuSO4 obtained theoretically, but that is the actual yield, and then what I did, actual by theoretical times 100, and then I got it. Did you understand? All right. Now the question here is about the bonding in the elements. They say this is a big one, basically, and this will be the last one. State what is meant by metallic bonding. They say. All right. They say state what is meant. They told you what is meant by metallic bonding. Now, in order to solve this, this is the answer basically. Check this out. This is the answer. I think everyone understands the two keywords down here. All right, what is it? Attraction and delocalized electron. This is very important. If you don't get bring these words on your answer, then you're not going to get even 1 mark. All right, delocalized is what? It's basically the electrons which have been lost by the metal in order to form the metal ion. So basically the attraction between, let's say, Na plus, and there is a delocalized electron, Na plus delocalized. So basically the attraction here between the positive the positively charged sodium ion and the delocalized electrons which has been released. This attraction is basically the metallic bonding. Did you guys understand? I think you know this. Now explain why the metallic bonding in magnesium is much stronger than sodium. There is magnesium and then you have sodium. Okay, Ilham, can you please try? What might be the answer? Tell me. Any idea? Ilham. All right, Sylvia, at least can you try? Look, one thing is pretty simple. Magnesium is more delocalized electrons, right? Isn't it? The reason why? Because Mg2 plus is being created. That means instead of one delocalized electrons, there are now two delocalized electrons, right? So obviously the attraction will be higher, and right, and since it loses more electrons, so obviously it will have a higher charge than Na plus. These 2 points must come in your answer. And the second part that must come, that is Mg2 plus is smaller than Na plus. Obviously what is happening here, two electrons are being lost from its outermost shell. So obviously what's going to happen, the attraction between the outermost shell and the nucleus is going to increase. So this will result to the decrease of ionic radius of Mg2 plus. Did you understand three of the points? These three basically contribute to metallic bonding, stronger metallic bonding. Tell me. Yeah, the radius is smaller, ionic radius is smaller. Radius increases, but that is Mg, this is Mg2 plus. Yeah, obviously. Yeah. Did you understand? All right. In what elements, silicon, phosphorus, sulfur, and chlorine, the atoms are joined by covalent bonds? Describe the attraction between the atoms in a covalent bond. They say basically. Please, they basically, in other words, told you to write the definition of covalent bond, and this is the definition of a covalent bond. You might want to write this if you want. It's taken from the mark scheme. Basically, they specifically wanted you to write this answer, and this is the official way of writing covalent bond definition according to the mark scheme. So please write this down. Have you written? It's the electrostatic attraction between the shared pair of electrons and two nuclei of the bonded atoms. What they're trying to say is that Cl. All right, this is two nuclei of the bonded atoms and shared pair of electrons. This is where electrons are shared. This bonding is covalent bond. Did you understand? No, electrostatic is important. Explain why the melting temperature of silicon is much higher than that of the phosphorus by referring to their structure. Please try to understand the question by referring to their structures, and you can clearly see that why silicon has a higher temperature than whom, than that of what, phosphorus, which is just 44 degrees Celsius. Why is that the case? Well, you just need to check out these three, all right, and then you need to talk about the structures, and the structures basically relate to the type of intermolecular forces present in them. Well, two things are pretty simple. First of all, phosphorus has what, a simple molecular structure, all right, and silicon has what, a giant covalent structure. Not okay, if you want you can give molecular, but better if you give when you covalent, when you write giant. Silicon has a giant covalent structure, all right. So when phosphorus melts, weak London forces are broken, and when silicon melts, strong covalent bonds are broken. This is very important. Remember, in simple molecular structures, only London forces are there. But in giant covalent structures, no London forces, just covalent bonds, right? And we know what? Covalent bonds are way more stronger than London forces, because it's a bond and that's a force. Obviously bonds are more stronger than forces, all right. So obviously you can understand why silicon now obviously has a higher melting temperature, because in order to break a bond, higher heat energy is required compared to breaking forces. Do you understand? All right, very good. So the next part, if we move on, the last part of this question, they said complete the dot and cross diagram of a molecule of sulfur dichloride. Use dot or cross for the chlorine atoms and crosses for the sulfur atoms, they said. So in order to solve this is pretty simple. So according to their conditions provided, we know that chlorine has what, 7 electrons, right? 1 2 3 4 5 6. For the seventh one is basically, being shared, and they say to show cross for sulfur atoms. So that's how we do it. And we also know that sulfur has about 6 electrons in its outermost shell, so that would be like this. One will be obviously shared here, and obviously you just follow the steps right here, and there you go. You can see that 3 of the atoms have full outer shell electrons. Now suggest a value for the ClS-Cl bond angle basically. Now uh, for this the bond angle would be 104.5. This is very important, that why this suggestion, like why does the bond angle is 104.5, because you need to check out one thing here. You need to check out that there are two bond pairs and there are two lone pairs, right? Well, check this out. In case of water, in water also we saw that there were what, there were two bond pairs, right? And we saw what, there were two lone pairs. So this resulted to the angle of 104.5 degrees. So by resembling the structure of water, we can basically, suggest a bond angle for this ClS-Cl bond. All right, so you have two lone pairs and two bond pairs basically. All right, so this basically causes what, this basically causes what, and we also know another thing, that what, LP LP lone pair bonding pair repulsion is greater than bond pair bonding pair, which is also greater than LP BP. All right. So due so these are the two things that you need to write. First of all, you need to suggest the angle, and then you need to say why you chose this and why do you think this happens. Because the third reason, which is pretty simple, because two lone pairs, you are going to write this. I mean, you are going to show this trend, and then you are going to argue that since lone pairs repel more than bonding pairs, the angle will get reduced from 109.5 to 104.5. Why did they say 109.5? Well, if you check out ammonia right here, ammonia had one lone pair. All right, since ammonia had one lone pair, the reason why it had the angle of 109.5 degree. Now the inclusion of another lone pair, increased the repulsion between them, and this basically reduced the angle to 104.5. All right, so this is how you basically write the 3 marks for this type of answer. So with this, our this class is over, and I will send you the two PDFs so that you can submit it by next week. Till then, bye.